Okay, my name is Scott Breitenfeld. I'm going to be talking about parallel compression I/O with HDF5, just some performance tuning techniques in this talk. And I have colleagues that we've worked on this project a lot, which is Jordan and Elena. So as an outline of talk, I'll just give an overview of compression and HDF5, especially about chunking considerations, since that's a key element of compression, especially in parallel. Then I'll go through some case studies of parallel compression in HDF5. So parallel in HDF5 is relatively new function. It was introduced in 1.10.2, so it's relatively new compared to the other features in HDF5 that we've been talking about. And so we're always seeking feedback on the performance that you're seeing in your application for parallel compression, whether good or bad, both. Current limitations of the parallel HDF5 compression is it doesn't support independent operations. So you have to use the when you create the data set, use the collective calls, and it doesn't yet support linked chunked I/O for reading. So we start with chunked storage. Basically, to get good parallel HDF5 compression performance, you got to start with a good chunking data set performance. So if you don't see good performance with your chunk data set, odds are compression is not going to be any better. So just as a reminder of what chunk data set is, so when you have a data set and you chunk it, it's basically equally divided into equally sized chunks. So for example, in memory then, you have the metadata cache, you have the data set headers, you have then a chunked index in that metadata cache that links to each of those chunked data sets in memory. Now, when you write that to disk then, which is a lower graph here, you have the file, then you have the header, which points to this chunk index, which then tells you where in this file the chunk for each one is written. So in each one of these are either written or read individually on a chunk by chunk basis. So going on with chunk storage then, so chunking is required not only for parallel compression, but also for any other filter. It's also, when you do I/O, you have to keep in mind that it's always performed on a whole chunk. So the size of your chunking could matter, especially with parallel compression, because you might be grabbing more of the chunk than you need. So that means that you have to either compress or uncompress that data set on a whole. You can't do partial decompression or compression. We have on our website, if you want to learn more about caching and cache chunking, I provided a link here. But certain things you want to consider when you chunk is how often are you going to access the same chunk? That might affect how much memory you need to do for chunking cache. If you're going to access it over and over again, you want that to be in the cache, so you don't have to go to disk each time. You also have to consider what the best chunk size is. So this is especially important for compression. If you have a very small chunk size, you probably won't get very good compression. And if it's too large, you might have issues with bringing in whole chunks and then having to do compression or uncompress that data. And just a reminder that the maximum size for a chunk is 4 gigabytes. That's the limit now. So with the study of the chunk, then you might want to adjust the size of the chunk cache size if you're doing a lot of partial reading of a chunk or a hyperslabs or a data set. If you're doing that a lot, you might want to mess with the chunk size. The default in HDF5 is 1 megabyte, which is typically pretty small, so you might want to increase that. And you can use that with these APIs here, set chunk cache for the whole data set or an individual data set. And then for the whole file, you can set it for set cache. That's for all data sets in the file. So in general, chunk size is important when you're doing partial I/O, because you don't want to keep bringing stuff from disk and then compressing it or uncompressing it. So you want to avoid that operation. So if it's in cache, you don't have to, you avoid that. As I mentioned with the 1 megabyte cache size, then you might not have that chunk be able to fit into cache. So you might want to increase it. If it doesn't fit, then all the writes are immediately written to disk. So with compression, then what that means is the entire chunk must be read or rewritten for every part of the chunk, every time part of the chunk is written. So the data must be, as I said, compressed or decompressed each time. And if you're doing non-sequential writes, that could result in a very large file, the normal. So without compression, the entire chunk must be written when it's first written to the file. If you have multiple chunks at once, then you can increase the cache size to hold more of those chunks in, so you don't go to disk as much. So it's just something to remember to play with the chunk caching if it's important to you in your application. So let's go on to studying. So now I mentioned that, well, how do you determine what's maybe the best cache size or what's the best chunk size to use? Well, we have an application benchmark that the HDF5 group developed called HDF5 IO test that explores the HDF5 parameter space. And what it does is a lot of the times users want to know, well, how is it best to organize my data? And this also is a tool that kind of helps you along with maybe what the best performing or you might get with certain parameters. So what this program does is it looks through all the different parameters. So the first parameter is dataset rank. So if you have a 2D array, you can either write that as a 2D array, or you can combine that into other data sets, which I'll talk about later. So the next step would be the slowest dimension. I'll talk about that next couple of slides, what that means. And then the storage layout, chunked or contiguous. For this talk, you're going to be basically focusing on chunk data sets to look at. And then you want to figure out if you want to initialize your field values. I'll mention that later in one of the applications that we looked at. The alignment in the file, do you want to do default alignment or do you want to use it on a alignment boundary? You can also select your metadata size. And then you want to check if using the newest library version of HDF5 helps your performance, or if you just want to use the lowest one that meets all your features. And then finally, do you want to do collective or independent? And for this, of course, you have to do collective for parallel compression. So just a quick talk about what that step means in the previous. So if you have, for example, you have 2D arrays and you have 5 variables and you have 2 time steps. So you have an option of rearranging your data or writing your data as either you can combine, the first column here is how you would just create the group, step 1, and then create the variables. You also have the option of collapsing those 5 variables and making it into a 3D array. And then you can also combine all those steps and make it into a 4D array. The other option you can have is if you separate it by variables. So here you have your variable 1, and then you can write for each time step those values. Then you can combine those instead and have 5 variables and then the number of time steps. And then again, you can collapse that into a 4D array. So you can play with all these different arrangements. And then we also have added compression to this HDF5 IO benchmark. So that's just an explanation of what that step of how you can rearrange your data. So what we did was we started on, this is on Summit, we started with the best weak scaling. So we scaled up the problem using HDF5 test on Summit. We chunked the data set. We did collective with no alignment. We did up to the rank 4. So what we did was, if you look here, the colors correspond to the rank 2, 3, 4. and then the time step is the purple and yellow, and it goes up to contiguous chunks, whether you did fill, whether you're doing alignment. For this, we didn't check the metadata, the library version, and then the independent. And what we did was rearrange those parameter spaces from the best scalability results all the way to the least scalable results. And this is the average time. So what we did was take this values of the best parameter space, which happened to be a chunk data set, because we need that for parallel, and it had to be collective. And for this case, we saw that the rank 4 array had the best scalability, and then the ranged them as a step. And then we also found that using no fill values also helped performance. And then we used the earliest library version. So with that, we turned on parallel compression and then did weak scaling with that best case scenario. So here I plotted the file size versus number of ranks. So 1. So the blue is no compression, and then the file size with compression. As you can see, it basically is proportional to what there was with no compression with compression. So you can see that it did help the file size. Then the total time with compression, and you can see that it scales. So after 168, you can see that it proportionally scales as you increase the number of processes. I think we had an issue with running on more than 21,000 cores, but otherwise, after a certain number of ranks, it performed fairly well as you increase the number of processes. And if you look at the weak efficiency, so this is relative to using 84 processes, you can see the improvement over this. So the compression is much improved over using no compression, which is the blue curves, as you increase the number of ranks. Another thing that we came across when we were doing parallel compression was that a lot of users, and sometimes we recommend this, is to create your data structure in your file itself as using one process. So in sequential mode, what HDF5 does, so if you do it that way, it allocates the chunks incrementally. So that means that when the data is written to the chunk for the first time, then it allocates it. And the chunk is, you can also initialize it with a default using a fill value. Now, if you did that in your parallel code, and then when you try to create it, when you try to call the MPIO driver, what the issue is going to be is that, well, those other processors don't see chunks that were already created. So what it's going to do when that happens is it's going to immediately allocate those arrays that were created by rank 1, and it's going to then try to initialize it, and then if you don't set a fill value, it's going to try to compress all of it, and that's going to basically 0, which is kind of a waste. And you can kind of see that we did a testing on blue waters, that if you have, so the blue, the yellow is the write original, and the orange is the open. So this is the total time to write it and then to open the file. You can see that it was taking forever on blue waters to do the open. As you increase the number of processors, it was getting even worse. So if you now turn off the never fill for the chunks, now you can see the lines here is the time. The green line now is the time it takes to do the open of the file, which is basically 0. And you can see that the write time actually remains constant. So the problem we were seeing is that, yeah, it was filling when the parallel processors tried to open that file, or open the data set, then it would create those data sets, write zeros, and then compress all those zeros. And that's why it's taking forever for the open original. So that's one gotcha that we kind of found, and you might run across if you're doing that now and then setting never fill. If you're creating all your data sets with rank 0, that might help your performance. So this is part of a lot of this work has been sponsored by the DOE, and we're still in the process of improving our parallel compression. So if you have, we're always, again, as I said in the beginning, always looking for good feedback, whether it's we're missing, you're not getting good performance with parallel compression, or you might want to just, or you're just starting to get started with parallel compression, then we can help with that. Other than that, is there any questions?
I have a question. Hey, Scott, thanks for the presentation. We've been using this data compression in parallel IO frequently recently. And when you mentioned that the field mode and compression, if you turn it off and the compression time is faster. But one question is, when you create a chunk, before you can write to it, if the field mode is not disabled, then I assume the HDF5 do use the default field value to fill the chunk. So one scenario is, what happens if the application doesn't write the entire chunk, and then you eventually need to compress the chunk? But if you didn't initialize it, what the chunk is the chunk containing some random value, then would that affect your compression ratio and making the data invalid?
So you're saying if you don't fill value, if you don't do fill value and you then compress that data that didn't have any value to it.
Yeah, because you need to pre-allocate the chunk in memory, and then you eventually need to flush it out. Doesn't matter the chunk is completely filled or not, or completely written by the application.
Yeah, Elena or Jordan, you can correct me, but I think it doesn't, if there's no value to compress, then it won't compress those values. I mean, there's nothing to compress, so it shouldn't affect it at all.
Yeah, I think we should distinguish between user buffer, right? And this is the responsibility of user buffer to fill it with the right values. So, but you are correct. If a chunk, for example, first of all, I always perform on a chunk. So that's why we have to read it before we partially modify it. And this is where performance will be bad, because you read, decode, override, encode, write back for the chunks. That's why it's important that I always perform on the whole chunk as much as you can. But what that field value on the opening Scott was talking about, that if you know that you will be writing the whole data set or the whole chunks, don't use field values, because on create, if you don't disable it, library will write those default values in the chunk. So yes, it will help with when you do partial IO on the chunks, overwriting values, then field value will be really written into the buffer, but it hurts performance. So it's user decision essentially in some sense. But if you know that you will always overwriting, don't use field value.
Okay, another question is disabling the field mode. Is it new, or is it already in the current release of the HDF5?
Oh,
no, it's pretty old.
Pretty old, yeah.
Yeah.
Mm-hmm.
Okay, thanks. I will give it a try, because when I try it, it seems like it's always on. Doesn't matter if I disable it or not, but I will give it a try and confirm it. Thanks.
I think we had a bug, I think you submitted a bug for that, I think, if I remember right. So.
Scott, and there is any time horizon for parallel lossy compression? I can take it.
What?
There is another from Lee. Actually, parallel HDF5 parallel compression works with the dynamically loaded filters. So one can use any type of compression. It should be registered with HDF5 if you want files to be shareable, so other people can find the same compression and use it. But yes, it is available right now, and there are several like SZ and ZFP compressions. They do have a lossy mode, so they can be used. One thing to remember: sometimes you have to preload those libraries for the nodes. So they are available, the shared libraries, or you can programmatically in your application to specify the path where to find the SO for filters.
Thank you.